Welcome to day 10 of International Virtual Workshop on Global Seismology and Tectonics. It is incumbent on me to mention that this virtual workshop has not just benefited undergraduate, postgraduate, and PhD students, but I have heard from several scientists and academicians profoundly acknowledging each and every lecture session. Some academicians have also sought to use the video recordings for imparting the valuable techniques and ideas to their university students. Being the convener of this workshop, such perception and commendation from people across the globe makes me swell with pride. I cannot thank enough to Professor G. Narhari Sastry, the director of CSIR NEST Zorat Assam, and to the formidable organizing team of this workshop for soldiering this great event. We have two lectures lined up for today. The first lecture shall be presented by Professor Tahmeed M. Al-Hussaini from Bangladesh University of Engineering and Technology. He is going to talk on new seismic design provisions for updated Bangladesh National Code with reference to seismic hazard assessment studies. Later in the evening, we have Professor Sebastiano D. Amico from University of Malta presenting lecture on the salience of computing seismic hazard maps and incorporating site effects. So the attendees are requested to resume later in this evening after the present lecture. Now may I request our session chairperson, Professor J.R. Kyle, for his initial remarks. Over to Professor J.R. Kyle.
Oh, thank you, Santanu. Thank you so much. Yes, at the outset, I must say that I know Professor Tahmeed for we meet at various seminars, international conferences, workshops, and things like that. And I know him personally because once he invited me as a keynote speaker at BUET way back in 2010, and I had been to his house, met his family. He is not only a great professor, but a great human being with warm heart, generosity, and above all, he is also a good teacher, very famous in Bangladesh University of Engineering Technology. So today we will hear from him on seismic hazards in Bangladesh. I think we have much to learn about seismic hazards, and Professor Tahmeed will enlighten us today morning with our very neighboring countries, how they have evolved the seismic hazard maps. And he is the key person in all projects, and we will be so glad, Professor Tahmeed, to listen to you. Thank you so much for kindly accepting our invitation. Thank you so much. Now the platform over to Dr. Santanu Barua.
Thank you, sir. Now may I request our co-session chairperson, Dr. Saurabh Barua, for his initial remarks. Over to Dr. Saurabh Barua.
Honorable Professor J.R. Kayal, the session chairman, today's guest of honor, our lecturer, Professor Tahmeed Al-Hussaini from BUET, Bangladesh, the convener of this meeting, Dr. Santanu Barua, and all my dear participants. Earthquake do not see the boundaries. 1897 earthquake occurred. Bangladesh, Sylhet region was totally devastated. And today with us, Professor Hussaini, whom I met in Indian Institute of Technology, Guwahati, almost 1.5 decades back. I still remember my interaction with him. He was really an enchanted personality with lots of wisdom. He has contributed to the seismic code of Bangladesh. So we are really eager to hear you, sir, in this platform, so that seismic hazard assessment map, what you have produced for Bangladesh region, may be also replicated in the neighboring areas of India. With that brief remark, I hand over the platform to Dr. Shantanu. Thank you.
Thank you very much, sir, for your nice comments. Now, I would like to narrate a short biodata of Professor Tahmeed M. Al-Hussaini. Professor Tahmeed M. Al-Hussaini obtained his BSc Engineering in Civil from BUET, that is Bangladesh University of Engineering and Technology, in 1984, Masters from AIT Bangkok in 1987, and PhD from Sunny Buffalo in 1992. He joined the faculty of BUET in 1994 and he became a professor in 2007. Dr. Al-Hussaini also served as the director for BUET Japan Institute of Disaster Prevention and Urban Safety during 2013 to 2017. For more than 30 years, he has been involved in teaching, research, and consultancy in geotechnical, structural, and earthquake engineering in Bangladesh, USA, France, Italy, and Thailand. In the US, Dr. Al-Hussaini was involved in NSF and NCER-funded research projects dealing with wave barriers for reduction of ground vibration and seismic response of base isolated structures. He was a visiting research scientist at École Centrale Paris in France during 2001 and in 2002 for the European project on control of vibrations from underground railway traffic. Dr. Al-Hussaini undertook specialized training on seismology and seismic hazard assessment in China and Italy. Moreover, he has published more than 60 research papers in different reputed journals. Now, I'd like to hand over to Professor Al-Hussaini for his presentation. Over to Professor Al-Hussaini.
First of all, I would like to thank the organizers for giving me this opportunity to deliver this lecture at this international virtual workshop on global seismology and tectonics. It is a pleasure for me to see Professor Kayal, who is an old friend of mine, and we have very fond memories of each other. And also, I understand that I have met Professor Dr. Borwa in Guwahati in 2007, and I thank the organizers for their kind words. In today's lecture, I will be talking about our experience regarding the new seismic design provisions for the updated Bangladesh National Building Code. And in this respect, I will also refer to seismic hazard assessment studies that have been done so far. I hope you are able to see and hear me clearly. If you have any problem, please let me know.
We can hear you properly. Please go ahead. Yes, nice.
So as you can see, actually I am a civil engineer, not a geophysicist or a seismologist by profession or background, whatever. But I have, because of my interest in in soil dynamics and earthquake engineering, I had this interest for learning seismic hazard assessment. And ultimately, I had the opportunity to do something in this regard for my country. So this is my table of contents, and first a little bit about the seismicity and the tectonics of Bangladesh, and after that the old building code, which is BNBC 1993. I will talk very briefly about that. Next, I will talk about the hazard assessment studies that have been done during 2010 and before 2010. I will be next talking about the updated design provisions, the change in the design provisions, and the specific new provisions in our new building code. There has been a recent change in the title of my talk. As you can see, it is now I am referring to BNBC 2020 because of a recent decision by the government that the code will be named as BNBC 2020. And that is the reason I made this change. So please refer to the updated code as BNBC 2020. And finally, I will be talking seismic hazard assessment studies and try to compare it with the updated code and end with my concluding remarks. So all of us know that Bangladesh is located near the colliding junction of the Indian plate and the Eurasian plate. And as you can see, there is a collision on the northern boundary as well as the eastern boundary. And it's a very complex mechanism, which other speakers have already mentioned in the previous talks. So here is a tectonic map. This is the direction of the plate. And as you know that, or you have heard already from a previous lecture by Dr. Borua, that it is not so simple, this plate movement at this junction. And there is some rotation also here. And there is some sticking and slipping, which is in a very complex manner in this region. There are some stars in this picture, which represent some major earthquakes. There are some lines which show some faults and anticlines and lineament structures. To have a more closer look at the available fault maps that we have. So you can see that the main fault is here. This is the plate boundary fault, may be conceived as a subduction fault. And there is an extension of it here. There are some other faults in this Chittagong Tripura fault belt. So these are some of them. We have the famous Dauki fault, this northeast. We have Dhubri fault. There are some other faults and some faults here, which is not presented here. Also here you can see some trace of a fault, which is not confirmed. It is not confirmed, but it is presumed that we have a blind fault here due to some earthquake that happened previously. And this is from the geological map. So on this map also we have some fault diagrams. So we don't have that much extensive fault mapping for our country. So some idea about the earthquake occurrence in Bangladesh and surrounding region. So the orange ones are 7 or 7 plus. The big ones 8 plus. And the plus ones is less than 5. The diamond is 5 and above. So we have. So as you can see, this whole country has some seismicity. There is no part which has zero seismicity. There is all of them have some seismicity and seismic hazard. So if we look at this figure, I think it is quite obvious without doing an analysis that this part, this northeastern part, is the most hazardous part. There is some confusion about the location of this earthquake, which is placed close to Chittagong here, but there is some controversy. Some says it's farther south, and also about the magnitude there is some confusion. Here is a picture showing the fault plain solutions of Bangladesh and the surrounding region. And you can see there are these strike slip solutions here, but we also have some subduction kind of fault plain solution here. So on this side, you can see there's a mixture of strike slip and reverse faulting, whereas in many places we have strike slip fault mechanism. Maybe there are some normal fault mechanism as well. This is the table which shows the different earthquakes which have affected Bangladesh. Starting from 1762, we have this Chittagong earthquake. The magnitude is 7.5, but I put a question mark. Somebody says it's bigger, and where is the location? That is also another question mark. We have the 1869 Kachar earthquake in India. That's about the distance from Dhaka. We have the Bengal earthquake, which is near the Madhupur blind fault area, somewhere close to that. So this distance is also not very confirmed, but we have some magnitude estimation. The great
You can't hear. Are you in the mute stage, Professor Tahmeed?
No. Can you see me now? Can you see the screen now?
Yes, we can see the screen, but
Okay.
can't hear.
Yeah. I was cut off temporarily. I was cut off, but I'm joining again. So it came automatically. So as I was referring, these earthquakes that is given here. The biggest earthquake is the Great Indian Earthquake, the 8.1 magnitude earthquake, and at a distance of 230 kilometers from Dhaka, the capital city. Dhaka is in the center of the country, and this is the magnitude. This is very big earthquake, 8 plus, and the yellow earthquakes that we have here are the earthquakes that are internal earthquakes. That means the local Bangladeshi earthquakes. So we have 3 local big Bangladeshi earthquakes. So that says that we have not only the risk from outside earthquakes, but also we have the risk from the internal earthquakes. So if we look at the dates, we can see that we didn't have any large earthquake in the last 19 years. So there is a chance that there has been stress build-up, and who knows when and where the next earthquake will take place. We hope it doesn't happen, but the reality is that we have the risk. Here is a isoseismal diagram of the 1897 Great Indian Earthquake, and this blue line shows that this big area inside Bangladesh had some damage to the masonry buildings, cracks, and here there is some photograph of a building in Rangpur which was damaged by this big earthquake. We didn't have that many structures of buildings at that time, but now we have a different scenario, and with all the vulnerable buildings we have, the scenario will be totally different for a repeat of this same earthquake. So that is our concern. Here we have the 1918 Srimangal earthquake, magnitude 7.6, which is a local earthquake. And this is some damage, local damage inside near Srimangal. Here is the 1930 Thupi earthquake in India, and this is the highest intensity. And if we look at this next intensity is 8. So that includes part of Bangladesh, and there was some extensive damage near Lalmonirhat and adjoining areas. We have several recent earthquakes. This is not a complete list, but these are some of the earthquakes that have caused some damage and not very serious, but there are some serious damage as well. And also this 2011 earthquake in Sikkim, magnitude 6.9, this resulted in a long duration shaking. So that is something that we should also consider in our design of our buildings, that when we have a long duration, it's a distant earthquake, long duration, long period earthquake. So that can have an effect, especially in our tall buildings. So we have now a lot of tall buildings in our cities. The epicenter, so that is a long distance, but you can see there was this building had some problem. So when your building has problem, you have damage, you have much more damage. So that is the point to see. And here you can see the vulnerable buildings, which are the brick buildings and also the mud wall buildings. We have many mud wall buildings in the rural areas which are vulnerable to earthquakes. Now, let me talk about the 1993 Bangladesh Building Code. As you can see, this is the first official building code. So this is the first building code. Now, let's look at the first seismic zoning map. But this seismic zoning map was prepared before the building code. So it is in 1979 and prepared by a committee under Geological Survey of Bangladesh. And one of my teacher, my Professor Jamilur Reza Chaudhry, was also a member of this committee. And this committee formed this map. And as you can see, the northeastern part of Bangladesh has the highest intensity, zone 1. And this is Dhaka is here. The second city, port city, Chittagong is here, is in the zone 2. And this is the lowest risk area in the southwestern part. This is the 1993 seismic zoning map, which is somewhat similar to this. There is some similarity, maybe some boundary change, but the difference we have is in the coefficients. We have some new coefficients which is relevant to that building code, and you can see the building code in 1993 had this formula where the building force is a function of Z. Z is here given here, so it is proportional to Z. So Z is the peak ground acceleration, which is being considered for design. So this is the formula, and if we will see later that for some cases you need site-specific studies. So this is a figure which showed that we difference between the new code and the old code. And this means the new code gives a higher value of the force compared to the older value. So this is a big difference between, especially when you have taller buildings, we have a bigger difference. So there is a need for change in the code. This, as I am a civil engineer, I am bringing up some civil engineering issues. I won't be dealing too much, just some idea. And here you can see that these are the three different earthquake resisting systems that are being used in concrete buildings around the world. And this one is the moment resisting frame, where we have the beams and the columns. And here we have also some additional bracing in addition to the beam and columns. So this is called brace frame. And in this, the lowest system, we have the shear walls. These are RC shear walls. Normally they are reinforced concrete shear walls, which are provided to resist the earthquake horizontal force. So this is the design response spectrum, and this is for the different soil types, S1, S2, S3. And for S4, that needs to be derived. So that is what was given in the code. So this code is quite similar to the UBC 1991 building code. Now let us show some results from seismic hazard assessment studies prior to our updated code. So this is in 2002. So here Bangladesh is divided into 1, 2, 3 zones, same as before, the same coefficients, but there is a change in the geometries. So this was proposed in 2002. This is in 2005, some other, there is differences in the methodologies. And here we have some different values of the peak ground acceleration for 475-year return period. This is from the G-shape diagram. I think it's for 475-year return period probably. And as you can see here also, the northeast has the highest hazard, but this is a pretty excessive hazard, I would say, compared to some other studies. And this is from our neighboring country, India. This is NDMA study 2010. This is a comprehensive report for the whole India, and I took this from the whole India map. And you can see the values of the PGA for different for a return period of 2,475 years. So here also this northeast region has a PGA of around 0.35 to 0.3. And in Dhaka, somewhere here, it's probably around 0.2 or something like that. In Chittagong, it's here. probably close to a bit greater than 0.2. And here you can see it is less, 0.12 or something like that. So here is our earthquake catalog, and which is used, and to get an idea of the attenuation, we studied these isoseismal maps provided by Professor Nandi in 2001 in his book, and using these historical intensity isoseismals, we also developed some attenuation law for our country, Bangladesh, and we used it some basis. So here the last one, these are the different attenuation laws used, and the last one is the one we developed for Bangladesh. And we have seen that whatever we developed has some good comparison with the other attenuation laws that have been used. So here is an example of the probabilistic peak ground acceleration obtained for a rock site. Means a very hard site. So this, as you can see, the highest hazard is in the northeast, and it's around 384 centimeter per second square. So it is not in G, it's in gals actually. So this is the peak value, and if you look here in Chittagong, this is the Chittagong area. Chittagong is here, so we have a value of 0.28 G, something like that, and probably Dhaka is somewhere here, 90, somewhere here, so probably around 0.2 or so. And if we go here, we have a lower value around 0.12 or less. And here again, we have a bit increased value because of some seismicity here. So this is our, gives some idea about the acceleration that can be expected from the different sources that have been considered all within and outside Bangladesh. This is an example which was done. It's not a recent study. It's an old study actually, a long time ago, and we did this in collaboration with ICTP of Italy at that time. And here we consider the recurrence of the 7.6 in Mongol earthquake. Gives a value of 0.25, but this is a design ground acceleration, not the maximum ground acceleration that we are seeing in the previous slide. Now, with this basic information, I move on to the seismic design provisions for Bangladesh. Here, this is, you can see it was submitted as BNBC 2017, but recent decision has changed it to BNBC 2020. It is now in press, so hopefully this year we will get the hard copy of this code, and it will be officially gazetted and a legal document. So what's new here? We have in this new code, we have considered earthquake. So in order to get some quantification, especially in the IBC 2000 in the US, they have used this 2% probability of exceedance in 50 years. And in some places in California, they've used the deterministic methods to get this maximum considered earthquake. But where they have not much information, they have gone for the probabilistic method, and that is 2% probability of exceedance 50 years. So that corresponds to a return period of 2,475 years. And in their code, they have taken the design ground motion as 2/3 value of this. In the Indian Building Code, we have the maximum considered earthquake, which is in the 2005 code, and we have the zone coefficient, which of this value surrounding Bangladesh. Now, let me share a slide which shows the real ground motion response spectrum obtained during the 2011 Christchurch earthquake. So all these lines, the curved lines, these irregular lines, these are the records. So the records is much higher than the design response spectrum, which is 500 year. So it's much above. Now, if the 2500 year response spectrum is plotted, we can see that this design spectrum corresponds much better to the 2500 year return period. So this gives some increased confidence that maybe this 2475 year or 2500 year return period gives a much better, much improved estimation for the seismic hazard. So now we have this proposed Bangladesh zoning map, as you can see, where we have the highest hazard in the northeast, and the second highest is here. The Chittagong is the second highest with the zone coefficient of 0.28. Dhaka is in 0.2, here 0.12. Again, here we have a higher value of 0.2. So here we are also saying, similar to the American code, that the design basis earthquake is taken as 2/3 of the MC. And if we now compare this with the Indian code, we can compare and we can see that, well, there is some good comparison here, 0.36 here and 0.36 here. So 0.36 we have here. However, there is some difference here, maybe some difference here, but there can be some local differences. That is always possible. If you look here on this side, this is 0.24 or around this. And if you look here also, we have 0.28 and 0.2. So average is also 0.24. On this part, there is some difference, 0.16, we have a little lower, so 0.12. So this is some difference here, but again here we have a higher zone value 0.2 and we have a 0.24 here. So I think there is some reasonable good agreement, though there are some differences, but there is some good agreements. And actually in developing the zoning map, we have actually considered many things. We have considered our studies, PSHS surrounding us. We considered previous seismic hazard assessment studies and the previous maps. So everything has been taken into consider. Some deterministic studies, everything has been considered. Zoning map. So now to compare between the new zoning map and the old zoning map, so we can see we had 3 zones and we are comparing the design value. So this is a comparison of the design, not the maximum one. So then this is 2/3 of the maximum one. So there is some good relation, but there is some differences. Some places there is some increase and some places some decrease. Especially here we have the increase, and here also we have some increase in these 2 parts especially. So here is a comparison of the old and the new. There is also compared with the 2005. I have taken 2/3 value of the Indian code to compare. And we have the 4 cities here. And here we have considered some comparison with some other studies. And here, finally, we have also compared with actually a report 2013, which has been done by Asian Disaster. So this institute has given some values which are much, much higher. If you look here, this is much higher. So Actually, there is some basic differences because they have considered some high magnitude earthquake sources, especially on the eastern region, eastern boundary. They have of Bangladesh. They have considered very high probable earthquakes, and that is the reason they have obtained these high values. So this needs to be remarked. So that's why I put it here. And here is the way the building code has classified the soil based on the SPT values or the undrained shear strength value or the shear wave value, and we need to consider the average shear wave velocity in a depth of certain depth. Normally it could be 30 meters or so. So that is something that is used. So here is the equation for the seismic design base shear. It is a bit different than what we used before in the 1993 code. So there is some change, and here we have the CS value, which is given here. And this is the response spectra for the different soil types. So we have these different soil types. Actually, these are taken from the European code. These are different soil types, and the response spectra features are taken from there. And these are the soil factors and the parameters for the shape of the curves. So here we have the importance factor, and in the new code you can see for ordinary building it is 1, but when we have important building it can be 1.5. So the force is multiplied by a factor of 1.5 when you are thinking of a important building or monumental building. For hazardous structures or hazardous storage housing facilities, we can have a higher importance factor as well. So that is will be on the judgment of the designer. So here is a table for the reduction factor R for different cases. And here is something new, totally new. This is called design category, seismic design category, which is used in the USA. And this design category classifies your particular project into a number, whether it is B or C or D. So if it is B, then you don't need to worry much. You have minimum design detail. But if it is C or D, then you need to worry. You need some seismic design detailing. Actually, this to tell it in easy terms, we need to provide some ductility in the building. Actually, it is the ductility that protects the structure from the earthquake. We have to understand that it is not possible or it is not feasible economically to design a building without damage for an earthquake. So that is not the scenario. So we allow damage in the building. So we have to provide ductility in the building. And if we have to provide ductility in the building, we have to follow certain seismic design detailing. So these are provided in the new building code. And in the geotechnical aspect also, we need to consider these things, that whether there will be liquefaction, slope, settlement, and the lateral pressure due to earthquake on the underground walls. And this kind of thing we need to consider. So these are some picture of irregularity which needs to be considered in the building, irregular shape, plan. And this is the vertical irregularity, different pictures showing the different types of vertical irregularities. And these are the, in short, the different concepts of the new building code. So I think I have talked some of this, but let me proceed. So here you can see that we have these dynamic analysis procedures which are used for our structural analysis, and we have two methods. One is the response spectrum method, another is the time history analysis. So there are some specifications how we will carry these methods and what kind of motion, what hazard we will use. So this needs to be clearly stated. Also, we have some new provisions for base isolated structures, for vertical motion, soft story, and also how we can use nonlinear methods, analysis methods for the building. So these are some of the references used in the seismic design provisions for the new code, and some acknowledgements. Now let me come to some recent seismic hazard assessment studies. So here is a study which is will be probably more interesting for you. This is a publication by Shiel et al. In 2014, and it's a probabilistic hazard map with a return period of 2,475 years for Tripura and Mizoram state. So here is Agartala. Agartala is very close to Brahmanbaria of Bangladesh, and here is the capital of Mizoram, Aizawl. Khagrachari is here of Bangladesh, Rangamati is here. And if we compare this with our code, so here some similarity we probably have. So in Agartala we have something 0.22, so 0.28, here is Brahmanbaria, so some similarity. However, here in the Sylhet is here, up here. So this is 0.5, so somewhere probably here we have higher hazard. So it is higher than what we have here. But here in the rest area, you can see here we have 0.28, 0.225, we have 0.28 here. So somewhere here we have 0.28. But here it's not so much, 0.17, 0.115. So this 0.2 is on the safe side compared to this. And this is the sort of comparison we can get. And let me make another comparison in the next slide. Northeast India by Dash and others in 2016. So this is the peak ground acceleration for a return period of 475. The Northeast India, the analysis for the Northeast India, the maximum PGA that he found was for 2,500 year is 0.5 G, and here is 0.323 G. So this is what he has. So in some places maybe you have exceeded your value of 0.36. But if you look at the table below here, for the main cities, the big cities, the Guwahati or Agartala or Aizawl, we don't have that high PGA, not as much as 0.15. So in Agartala, we have 0.217, and in 2011 NDMA is 0.18. According to Indian code, it's Z by 2, 0.36 by 2, 0.18. And let me see what we have from our BNBC code. So for our BNBC code, Agartala is very close to Brahmanbaria. Our design PGA is 2/3 times Z, so it comes to 0.19. So I think 0.19 is comparable to all these three values here. It's to be noted also that there are definitely some other studies which give much higher hazard values. So there are differences in the hazard methods and assumptions. So it's actually a big responsibility to make a comparison and see why the difference is there and what would be a more realistic assessment. So these we have different studies. It's not possible to present all of them, and I am not also presenting all of them. And there is differences, and some of the differences we know why they are, but some maybe not so very clear. So here is some results from some research collaboration that we have with University of Trieste in Italy. So this is some recent results. So this is called this is a deterministic approach. It's called the neo-deterministic seismic hazard assessment, and we have our Italian colleagues visiting us in BUET and in 2017. So we had this research collaboration ongoing, still is going, continuing, and this is a little brief. So this is a physics-based approach. So it's a mathematical solution of the wave propagation problem, and it's described here. And here is an example which shows that sometimes the PSHA maps can miss something. But the deterministic method will probably not miss that. So because it considers all the faults, but here there are some assumptions and sometimes some is missed. So let us look at this point here. According to this map, this PGA is less than 0.15 G. According to this map, this PGA is around 0.2 to 0.35 G. So what happened? So when we have this earthquake, magnitude 6.1 earthquake in this region in northern Italy, we had this value of the ground motion. So the actual ground motion exceeded 0.25 G. So this is actually much greater than this, and this is more comparable with this. So this is an example that how PSHA hazard maps can sometimes underestimate the ground motion. So these are some structure models considered for Bangladesh, and there is also a part of India here. And these are the seismogenic zones considered for the Bangladesh study. And here is some value considering all the sources as a combined map. And this is the design ground acceleration values. So as you can see here, these values, these are all design value. So we compare it with the design value in our zoning map. So this value is in this range 0.1 to 0.2. So it's around 0.15. So if we compare with our zoning map, also in this region, we have something like 0.13 G. So there is some good comparison here. However, in this region, there is some big differences. And here, especially here, we have this Srimangal earthquake, we have this Chittagong earthquake and things like that. So there is some differences, and what I have summarized here that in Sylhet city, this PG design ground acceleration can be 0.3 to 0.63 G. So it's much exceeding. In Chittagong, also it is more 0.3 to 0.4 G. So these values is far exceeding the design PGF values in certain regions. So also here is another plot, recent plot, and here this is some idea of the acceleration, the peak ground. This is a spectral acceleration plot, so our peak ground acceleration is somewhere here. So we can see that it's in the range of 0.5 to 0.7 G, the ground acceleration, due to a magnitude 7.5 earthquake on Dauki Fault at a depth of 15 kilometers. This gives up to 0.7 G in Sylhet city for certain conditions. We have studied various different conditions. So this is the extreme condition that we obtain, and as you understand, if it is 8 magnitude earthquake, it will be much higher. But we have heard a lot of talks about Dauki Fault, so I thought that I present this graph as well here in this talk. So here I'm coming to the end, but before that, this mega earthquake scenario by this recent paper in 2016, and this graph gives a big. I would say it has created a lot of panic. I would say that nothing will be there if such an earthquake happens. And it says that a 8.2 to 9 magnitude earthquake can happen anywhere in this shaded region. So that is something we cannot imagine actually. And I won't discuss much about it, but I would like to say that there is no historical evidence yet, and we need to do a lot of much more extensive validation and cross-checking about what has been done. So here we did some simulation that if we have a big earthquake, 8.5 earthquake, what happens, and if we have 8 magnitude earthquake. So you can see that for such big earthquakes, we can have a very large ground acceleration. So you can see it can reach 1 G at certain points. So this is very huge earthquakes. And also in your talk, you have I have heard about the stones being thrown upward by the big 8+ magnitude earthquakes in Assam and adjoining regions. And so here also we see the same, that it is possible to have these large earthquakes, large ground acceleration. So this is to give an idea that we are saying, okay, that this big earthquake can happen. But when you consider this, then where do we stand? What are the engineers faced with? So we have to be realistic in what we are saying before coming to a conclusion. So my final concluding remarks, we have a very challenging problem. This is a complex stress zone, complex slip zone, complex sticking zone. There is subduction going on. There is tectonic subsidence going on in Bangladesh, and it varies. The GPS movement varies from place to place in Bangladesh. So it's a complex slipping and sticking mechanism, and it is indeed a big challenge, and I think there is a lot of scope to improve on all the work that has been done so far, and the uncertainties need to be dealt very carefully. We have saying that PSHA based seismic hazard maps can have underestimation of the seismic hazard in several recent major earthquakes. And for that, it is what I believe, and many of my colleagues also believe, that deterministic seismic hazard assessment methods should be used in conjunction with probabilistic methods for developing the hazard maps. Otherwise, we may miss some risks. The NDSHA studies that we have conducted is indicating higher seismic hazard than code provisions. The recent publication in 2016, which states or mentions about lock stresses beneath the delta sediments, raise the possibility that there's seismic hazard may be more than what we are estimating now. But how much more, that is something needs to be validated. So it is my personal opinion that the possibility of a mega earthquake deep inside Bangladesh is questionable. And we should also understand that a mega earthquake can easily result in extreme PGF values way beyond our building code values. In Bangladesh, we have a problem with our fault mapping. There are a lot of faults which are blind faults. So whatever fault maps, these needs to be carefully confirmed. And there are differences in different publication, different fault maps. And there is also the controversy about the length of the faults and the exact location of the faults. So to summarize, more seismological studies, critical evaluation and validation is necessary to address the emerging question of big earthquake event. Because some study is suggesting this, so we need to address it. And what kind of down motion values we expect. We think we need to work hard in this regard, as we don't have time to waste. With this, I would like to thank you all. This is a photo of our university. Actually, it is our department building, civil engineering building. And I hope that the participants of this lecture have a chance to visit us here in Bangladesh. And I must thank you all for your patient hearing and being with me during this long talk. With this, I think I should close my sharing, right?
Thank you very much, sir. Actually, Dr. Santanu has to leave due to some unavoidable circumstances, so I have to take over from here. Thank you very much, Professor Tahmeed Al-Hussaini, sir, for sharing your immense knowledge on the seismic code and seismic hazard assessment scenario of Bangladesh, and as well as the tectonics of Northeast Indian part, Northeast Indian subcontinent. So I would like to request Professor Jay Kyle, sir, for his initial remarks on this talk.
Yes, thank you so much. I think, yes, it was a wonderful, much informative and educative lecture by Professor Tahmeed. We all expected that he will really enlighten us, and he did. And I think he has touched upon many points. And his last concluding point, remarks on the mega earthquake in Bangladesh is similar to that of mine. I was also very much, I could not understand how an interpreted zone can create such a mega earthquake. Mega earthquakes are normally in the subduction, big subduction zone, like that of Sumatra, like that of Japan Trench, like that of Alaska Trench or Chile Trench. So it was a bit, I could not reconcile with this paper how it can really be in the realistic sense, how it can happen. So I asked some of my student and colleague to recheck their GPS data and see what is really the story. Now, in a recent publication in 2020, just a month ago or 1.5 months ago, they have published their Panda et al., Panda, Vinith, Bhaskar Kundu. This paper has come in Tectonics, and they found that the plate motion was estimated much higher than what it is from their observation. So practically they have ruled out such possibility of mega earthquake in an interpreted zone that in Bangladesh. Anyway, so you have shown the scenario what can happen with a 7.5 magnitude or with 8 magnitude, how much it can, acceleration can go up. And 9, of course, as you say, questionable. That is also, we understand it's questionable. But my query to Professor Tahmeed is that, yes, you have done a tremendous job for your country, and you have come out with a new design code, which is now stamped, gazetted by the government of Bangladesh. Now, with this new design code, maybe your new buildings, new construction will be followed by this new design. But just my query is how your old buildings, means retrofitting problem or retrofitting scheme, how it is taken care of in your country. Are you going to take some action on this retrofitting of the old buildings which are not properly designed to withstand a large earthquake? What is your comment on that? Professor Tahmeed, please.
Yeah, thank you, Professor Kayal, for your remarks. Yes, in Bangladesh, we have actually done several retrofitting works. Especially this happened after, the collapse of a garment factory. This happened in 2013. There was a collapse of a 8-story garments factory building, which resulted in the death of more than 1,000 garment workers. So following that, there was pressure to re-evaluate the safety of existing garment factory buildings. So a lot of work has been done in this regard. Our university, as well as other engineering firms, have done a big job in assessing the seismic safety. So when you are doing assessment for the existing buildings, it is not like designing new buildings. So the approach is different. So the approach is to look at the realistic loads, the realistic building loads, and the realistic safety issue. So this has been done, and there has been several buildings which have been retrofitted in recent years. Regarding other buildings, only very few have been done. But I think we'll have more retrofitted buildings in the future. Specifically, recently an assessment of school buildings is undergoing, and these buildings are not safe. So yes. I think next would be probably retrofitting of school buildings. Probably.
Thank you so much, Professor Tahmeed. Now I hand over to the organizing committee to carry on the questions from the participants. Please carry on, Mr. Clear.
Thank you, sir. Sorobora sir for his comments. Over to Sorobora. Okay, maybe Dr. Sorobora sir is a bit busy. So I'd like to request Mr. Prasudya for the question and answers. Over to Mr. Prasudya.
Thank you. So with your respect, I'm going to read out the questions. So the first question is in the slide 19. Based on what factors one decides regarding selection of building types in seismic prone areas out of 3 building types?
can you repeat which slide exactly?
It says slide number 19.
I cannot remember the number, but if you can mention which, what is it describing?
I can repeat the question, sir.
Yeah.
Okay.
Repeat the question.
Okay. Based on what factors one decides regarding selection of buildings type in seismic prone areas out of 3 building types?
Okay. Let me check. Just a minute.
Professor Tahmeed.
Yeah.
Yeah. If I understand the question, possibly the participant is asking, you have shown.
Okay.
three
Now
types of-
I understand. Yeah.
Yeah.
So actually, there are 3 alternative choices. Actually, these are 3 choices. So you can go for either one of them. It is your choice. The designer has the choice to use 3. But you know, if it is very seismic, so maybe you need to go for the lower 2. So that is possible. But normally we have the top one, the moment resisting frame. That is the common practice. Did I give the answer?
Yes, sir.
So, yeah.
So the next question is how Z values for different zones are calculated?
Okay. In this Z value has the relation with the probabilistic ground acceleration obtained for a return period of 2,475 years. So that was one of the basis of the zone coefficients.
Okay, sir.
Please.
The next question is how new building codes take care of the area covered by alluvium deposits and loose soil.
Yes. As you can see in my slide 36, I am looking at my slides. So in slide 36, I presented a table which characterizes how the soil can be classified into different classes. So for different classes, we have actually different response spectra. So this is in slide 39. So we have different response spectra. So different response spectra will have different effect on the building. So it's not the same. So the site effect is embedded in the response spectrum when we are doing the response spectrum analysis, and when we are doing static calculations, then we have also the factor S. S is the soil factor which is used. So if S is more, your force is more. So this is in short the effect of the soil.
Okay, sir. The next question is which site characteristics parameters you have considered for PSHA study over bedrock level?
Which?
PSHA studies.
No, which? No, can you repeat the question?
Okay, which site characteristics parameters you have considered for PSHA studies?
Okay, yeah. This is for actually rock, hard rock. So it's no soil, it is rock. The values that we have obtained is for rock.
Okay, sir. I think that's all the question.
Thank you very much, Prasidya. Now I think the session is almost over, so I'd like to offer the vote of thanks on this occasion. I am very much privileged to have you with Sir, Professor Tahmeed Al-Hussaini, sir, for presenting us with the immense knowledge of yours regarding the building codes and seismic hazard assessment and other different types of hazard assessment studies. For being with us today. I affirm a sincere sense of gratitude to Professor J.R. Kyle sir for chairing the session and being always with us during this webinar session. I would like to thank Dr. Sorobura sir also for being with us and giving his remarks on this. Thanks goes to the convener of this organizing committee, Dr. Santanu Barua, and also for Dr. G. Narahari Sastry, Director CSR NIST, for being so supportive and encouraging us to organize this webinar session, and also the participants without whom this would have been a failure. Thank you very much. The session is over now. Thank you, sir.
Thank you all.